Why are you chastising me?
Chastising?
Look, you say with math,
Jasmine, do you mean
nothing.
chastising?
Chastising. What did she say? I didn't say.
Chastising.
That one was recorded too.
That's not stubborn to how.
You know what sucks? When I want to hear what I say in recordings,
You make me
for
feel
some
very
reason, I'm
minute.
just really quiet.
Yeah.
Yeah. Well, people around me are just really loud.
What?
No, because I said something in physics, and I was sitting right in front of the room.
You said
and
something.
I wanted to come back and I wanted to hear if I said it. And, like, it was
I'm
there.
sure you said it.
Huh?
He did say it, but it's
But
probably
you couldn't
not
hear it.
loud
Yeah.
enough. You were like right in front of the board though.
Yeah, but everybody else behind me was louder.
I remember.
All right, let's take a look at an example of
Too many
a
people.
balloon. Okay? So I'm referencing, in case you're wondering, number 11 on page 251. Remember these problems I told you the other day? Again, there are a lot of good problems in here. This is number 11. It says, a spherical, which means obviously like a spherical. A spherical balloon is inflated with helium at a rate of 100 pi feet cubed per minute. How fast is the balloon's radius increasing? At the instant the radius is 5. How fast is the surface area increasing at the same instant? So, we got the balloon increasing its volume, or filling up, at a rate of 100 pi cubic feet per minute. So already, I know, see, I should write these in words, shouldn't I? Let me write the words out, only because,
It's just gonna help just a little.
Just because you can see it, like, right in front of you.
You guys, let's just.
balloon 1 L or 2 L's? 2.
It's 1L, what are you talking about?
Who sings that again?
I'll be recorded, just so you know.
Oh,
Like,
right.
you know how they have like American Idol, their special American Idols just
I
like
love
that.
80s music. Who doesn't love 80s music?
When it's
Depends
sung by
on
the
what
people from the
kind of-
Phil
80s.
Collins,
When it's sung by you, it's just
Dion,
like
Kenny
dead cats.
Rogers. Come on, people.
No, you're right, Justin.
A spherical balloon is inflated with helium at a rate, or at the rate of 100 pi cubic feet per minute.
So that are D.
Okay? Let's just, hold on for 1 second. Let's write it all out first, and then we'll
Hold
discuss.
on, Kenny.
That's our DVD.
How fast is the radius of the balloon increasing when
I said R because it said rate. Here,
or let's use
not cashew.
at the instant it is 5 feet how fast is the surface area increasing at the same moment or instant?
But it's not the same as the derivative and
How fast is
I already think what I can see is never ending in the morning.
Start doing it. Figure it out. Okay.
Wait, what's the formula of balloons?
The sphere, what's the sphere?
So,
We need to know the sphere though.
It's like
Isn't it
4/3 pi r squared
volume.
to the third power.
It's gotta be cubed because it's
Yeah.
only R, right?
Yeah.
All right, so the first thing, yes, you do have to know is your volume formula, but let's start over the problem. Spherical balloon, dreads. Remember dreads, guys?
Diagram,
Related
Rate.
equation,
equations,
Diagram.
surface
Derivative.
derivative, and
Summation.
solve and substitution.
Solve or substitution, good. Either one, both.
Dread.
It is
So-
deep.
It's a spherical balloon, so diagram-wise, people,
So balloon. There you
It's a circle.
remember a sphere? You always draw like that, okay?
Another circle. It's like.
It's got a radius, R. Call that R right there. It says, a spherical balloon is inflated with helium at the rate of, so that must be what?
the rate of,
A rate of change. Of what though?
DVDT.
Why is it dV dt? Why not ds?
Because it's time.
Because of not, no, it is always T, but why is it dV and not like
Oh,
d?
because it's velocity.
Volume.
Because of the units. Look at your units.
Right next to my question.
Cubic feet is volume. Minutes is time. Volume over time means dV over dt. Again, feet cubed indicates volume. Minute indicates time.
So that's what it
Oh, no, I think that's really good.
Now, dV dt again is equal to 100 pi cubic feet per minute. Now, it is increasing or decreasing.
Increasing.
Why, Kenny?
Yes, it's increasing. It's
No,
inflated.
no.
Inflated.
The radius I'm saying.
Oh, inflated.
Inflated.
Yeah.
Okay.
I thought increasing.
If it said it's being deflated,
Yeah.
the rate would have been what?
Minus.
Negative. Again, if this problem had said it's decreasing, yes, Rosie, but negative. If it had been deflating, take a balloon and let air out. What happens to the volume? It goes down. So it's decreasing. So this would have been negative there. Next. What is the thing for part A that I'm looking for?
DR dt.
Radius.
DR dt.
Why dr dt, Carrie? It says, how fast is the radius of the balloon increasing? Which is dr, the change of the radius, with respect to time. So that's my goal. I'm listing my rates first.
No, okay, fine. I was gonna ask you about the 5 feet.
That's where I'm gonna,
Yeah.
give me a sec there, yeah. So I'm listing my rates. My rates are volumetric, I know what it is. My linear rate, or my rate of change of the radius, is unknown. That's what I'm gonna solve for.
You're
Okay.
trying to find R.
No, you're trying to find
DR dt?
the RDT.
No, it never.
This is R,
Well,
right
it
here.
is, it is.
See what I'm saying now?
Yeah.
Okay? It says, find how fast the radius of the balloon is increasing at the instant that it is 5 feet. So this is the radius here. This is the radius they're looking for. And you're going to see where it comes into play. Let's go through this now. The third part is equations. So I've got, again, D for diagram, R for related rates, dV, dt was 100 pi cubic feet per minute. dr dt was what we're looking for. Okay, we also leave the 5 alone for now.
4 pi.
Okay, let's start by writing our formula. Volume equals 4/3.
Oh, pi.
I, R, and they're
Cube.
Okay,
H.
now, no H, it's a cylinder. It's not a cylinder, it's a sphere.
What is
Okay.
the cylinder was beginning?
I don't know.
I think it would be.
What?
I don't know if this is given on the AP exam or not.
Yeah, can you give us?
I'm not sure if it's given on the AP exam or not, guys. Ooh.
So that means you can't
It
get
would,
rid of
well, yeah, it is, when you separate it, you can.
Let me look it up tonight and I'll let you know. Okay? If there's a doubt tomorrow and you think it should be given, I'll take a look and see. Okay? If it is given, it's given. There's certain things you gotta know though. Like, for example, rectangle. What is that? Volume.
LV, LW.
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 X, Y,
But the
Z.
volume of rectangle is solid.
X, Y, Z.
LW, H, or XYZ, sure.
But those are simple ones like triangle
That's what I'm saying. The simple ones you gotta know.
and cylinder.
Okay, cylinder, you gotta know what the volume is. It's pi r squared, which is a circle, times the height.
Yeah.
Now, at this point, I've got my equation. What does the E stand for in dreads? I'm sorry, what does the next D stand for?
derivative.
Derivative or differentiate. So, implicitly derivative. Implicitly. What does this become?
dV
That's what it was.
dt.
dV dt equals 4/3
What does the R cubed become?
dVr.
R squared.
R squared dV.
No, yeah, R.
I'm leaving this alone as a constant for now. Just tell me what R cubed becomes. 3r to the second,
dr dt.
dr dt. Because remember, with these, we're doing everything with respect to time. So not only do we take its derivative, but we also apply a rate of change with respect to time of whatever that may be. Now, what you notice, as many of you noticed already, is the 3's cancel. 3's cancel. Everybody see that? Maybe not. So you're left with 4 pi r cubed, r squared. 4 pi r squared is what again, Gary?
Surface area.
The surface area of a sphere. Again, and that's going to be asked for in what part, guys? Part B. How fast is the surface area increasing? So let's keep that in mind for a little while, just in the back of our heads, okay? Next, at this point in time, I know dV dt. It's 100 pi. I know what R is. What is R?
R is,
R is fine.
Yeah.
Remember before you kept saying the radius here? In this problem, go back. DRDT we're looking for, so we don't know that. But we do know at the instant when it's 5. Well, what is 5? R is 5. Okay, at the instant, how fast is the radius? So we're looking at the radius of the balloon increasing when it is 5. So the radius when it's 5. So go back down here.
Like you have DVT for 100 pi feet square, and then you have it again.
Oh, wow.
I took the derivative of this.
Right, so why do you have, but why do you have DVT that it equals that?
Because I'm going to plug that in. It's given in the problem. This was given in the beginning. It said the volume. It says, I'm going to do it now. It says the volume is changing at a rate of 100 pi. So at this point, people, let's plug in, or we can actually solve. Okay, notice the pi is going to drop off, please.
That should be DR.
So notice, where did I sub in? I subbed in for dVdt, because that was given in the problem, with the rate of change of volume. I subbed in for the radius, which was given as 5. Notice I keep my units here, because it tells me I've got feet squared over here, I've got feet cubed per minute over here. So my answer, 2 of my feet are going to be gone. Not feet like that. 2 of my feet are gone, I'm left with feet per minute. And dRdt should be feet per minute. How does the radius change? In feet. How does time change? Per minute. So my answer will have units of feet per minute. And I can see that clearly.
And they would ask you also in the, it says, they ever ask you to convert minutes to seconds or hours?
Not really.
Just asking, I mean,
Do you
I know-
think, Anna? Any questions for me? Okay. If the problem gives you in minutes, then it's going to ask you the answer in minutes. It's not going to go from minutes to seconds like that.
Okay.
Okay? That's not testing your knowledge of calculus. I get what you're saying. Cancel the pi's, please.
We don't want to go back.
What does 4 times 5 become?
100.
No.
What?
20.
Wait, I'm supposed to do the exponent first?
What? Oh, jeez. Sorry. Thank you.
Yeah, 25.
Thank you. You know why I screwed that up? Why did I screw that up?
Because you thought 4 times
Did you do
4,
extra?
5 times 4.
Because I saw the feet beforehand and I put the square on the outside, which is what you're supposed to do, but I just saw the 5 feet, didn't even think of a square. Okay? Yes, 5 squared is 25.
Times 4 is
So this is 25 times 4, which is 100.
pi.
No, pi's are gone.
Oh, never mind.
I cancel
The
both
R
pi's.
anyway.
You would have. What does the RDT turn out to be, guys? 1.
This is me. Over there.
Wait, but after you get 1, do you have to plug it back in?
Now, that's part A.
Yeah.
Part A.
That's part A. Part B asks us, find the rate at which the surface area is changing. Surface area is S, right?
Yeah.
So if I know what the surface area is now, remember the surface area is 4 pi r squared. If I want to find the rate at which this is changing, I differentiate.
And then plug in. Right?
Do you still put the R that you already have?
Now, here's the tricky part. Here's the tricky part. Again, if I implicitly differentiate, this becomes 2r dRdt. We have dRdt from the first part. Without solving the first part, you can't get the second part. Remember we just got 1 for dRdt? So you got to put a 1 there, and it says the same instant. It said, the problem said, how fast is the surface area increasing at the same instant? So the radius is still 5. So 5, 1, 2, 4 pi. 4 by 2 is 8. 8 times 5 is 40. 40 times pi, 40 pi. Now, before you leave, units, surface area
B squared.
per. Good. Again, because ds, this is really, if you want to call it dA, you can. I call it S though, but it's area. Sometimes people see the S and they get confused. S is surface area.
Good S-A.
Okay? You can call it SA if you like, sure.
Alright.
Go on, work, it's fine. See you tomorrow. What are we going to do next?
How's that relative?
Linearization? You want to do an example of like the square root approximation one? Whatever.
Anything that you would give to us on the
I made your questions up a while ago when I made the notes. I don't remember what your quizzes are. It could be anything. Anything at all. imagine if I had, I don't know, square root of 50. And I wanted to figure out what that is. I can use my calculator, obviously, but I can do it also with linearization or differentials. So, how do we start this kind of a problem, Edgar?
We were talking about how much you took for system.
So what's the number that we're going to use? Okay, but what's the number under the radical? The radicand going to be? Radical what gives me 7?
Oh, what? Oh, what is this?
What's the closest perfect
49.
square? Thank you, near 50, 49. So, we're going to...
That's you.
We're going to use radical 49 as our estimate. Okay? We start by saying f of x equals radical x. Because again, Rosie, what are we trying to do? We're really trying to plug in a 50 here to see what we get. So that's the function we're looking at. To do this kind of a problem, the easiest way to do it is to write it as a derivative. So take the derivative now. And write this, instead of f of x, write it as like dy dx, like that. Okay, so even if you want to call it, instead of f of x, just to be clear, if you want to call it y instead, that's fine. So we take the derivative on that side, dy dx. What's the derivative of this? What is it really?
X of
Be careful. Radical x is really x to the 1/2, right? So how do I take the derivative of that, Rosie? You bring it down by 1, you bring it down and reduce it by 1. Very good. Again, that's what I have so far. Now, what I want to do after that is say to myself, I can move the dx up. So I'm going to write dy equals 1/2 x to the negative 1/2 dx. Now, x to the negative 1/2 is really like putting it in the bottom, isn't it? Making it positive. So I write it as dy equals 1 over 2x to the 1/2 dx. But isn't x to the 1/2 really radical, like we said a minute ago? So I can then write this like this. And now the problem becomes this. What was the perfect square that we knew? What was the number that we knew that we said we're going to use? 49. So take that and put that in for your x there. Now what the heck is this dx? What does that actually mean? What does dx mean in calculus?
Break it down.
Edgar? What does dx really mean?
Everybody nice.
Mike got the joke.
I don't know if it's on. dx dt would mean that, not this. What does delta x mean? The delta or the change in the x, right? dx is like another change in x, but it's a smaller one. So what I want to ask you is this. How far did my value change from what I had to what I used? What did it change by? How do you go from 50 to 49? Change by 1. So that tells me that for this problem, I could have written in the beginning that dx, in this case, we're approximating 50, dx is 1. Because I went from 49 up to 50. So here, Rosie, I'm going to put a 1 in for dx now. Again, because of the fact that it came from that problem. Now you can figure this out. What's the square root of 49? So this becomes 1 over 14, right? So dy is 1 over 14. Well, it wouldn't be given like this because this is too hard of a decimal to figure out. But if you know what this decimal is, you could type in 1 out of 14 and you get a value as a decimal. Let's see what we get for 1 out of 14, unless Edgar can do it in his head. Oh, 0714. Wait, no. Like that. Now, what the dy means is this. It means that, what's the square root of 49? It's just 7, right? So my answer is going to be 7 plus an additional whatever's here. So the square root of 50 is not 7, but it's 7.0714.
That's the square root
That's the approximation of the square root of 50. We take whatever we get, which we know is 7, it's our starting point, and we look at our dy. And use logic. If you subtracted this number, it would have been if you were doing like square root of 48, because it's got to get smaller. But the square root of 50 is going to be bigger than 7, right? So by logic, you need to add it. Okay, you need to add it. And if you go to your calculator and type in radical 50, we have 70714. So we want square root of 50. No, square root. There we go. 7071, and we're off by there. See, that's very close. We had 0714. This is 0710. Look how close they are. Our approximation and theirs. Now, you're not going to be given something with 1/14 ever, because then you have to use your calculator to find out the value anyway. Okay? Try to figure out the square root of 63. I'm going to use the bathroom real quick. Edgar, make sure it's good. Rosie, are you good so far?
Yeah.
Try the same thing we did, but with 63.
So you guys really didn't get my joke?
No.
When you said the X?
No.
Think about it, but.
No.
You never watch wrestling?
No.
Blind.
I don't really watch.
Huh?
I don't really watch.
So you never seen wrestling?
No, nigga. What I saw was Batista and John Cena.
That's what I'm talking about. Before
I saw
that,
that
DX.
plays.
Remember?
No.
You don't? Rosie, you know what I'm talking about? No, it's just Christian.
There's Revolution on Triple H.
Huh?
That is Triple H.
Triple H and Shawn Michaels.
There you go.
Yeah, it's like, I was singing the theme song. You guys are funny.
Right here, quick.
Who's that?
Edgar, if I use one.
No, Rosie.
Cause look, it's
Then you
63.
do minus
In
negative
minus
one.
negative one, okay. So dy would be negative 1/16.
And that's for the viewers subtract in.
What? Okay. Let's go when I put negative, I'm saying negative upon minus negative.
Oh, but you had the negative.
But look, the real one is 7.8.
No, you, this time instead of minus.
Oh, it needs to be plus always, no matter if it's negative?
Yeah. Plus negative subtracting it.
Oh, okay.
And it's almost exactly.
Yes, please stop. No, what's so good about it?
It's just like pretty much a better camera, better processors.
See, I'm about to see right now. YouTube. So I heard that the whole thing about the iPhone was
It's the 5 megapixel inside camera and an ultra fast 4G LTE if you plug in the right SIM card.
Okay.
Should I do it on the board?
Oh damn, I have to plug in a SIM card in this thing or something.
Alright, now I want you to find this one.
Do it on the board.
Now, Rosie, what's the number that you think is closest to the X square root? What's the X, what's the delta?
Five.
I'm gonna actually do that part. I thought you were going down, I got it different.
Sixty-six. Oh,
Keep it. What number,
it's not full name.
what number to the third power gives us, it's equals to 66.
You just couldn't.
Yeah, no, yeah, I know, I should put it, you were just saying right. I think Mr. Hauser's in trouble with that. He's taking too long. What do you think he says?
130 minus 1 and then 230.
Yes. What's the number that you found?
Oh, I didn't think that. I don't know my phone.
Actually, no, that would do and give me, maybe they will actually. Just start from 1. 1 to the third is 1. 1 to the 2 is 8. 2 to the third is 8. 3 to the third is 27. 4 to the third is 64. 5 to the third is 125. So what do you think?
I bet there's gonna be stupid.
What?
I bet there's gonna be stupid.
iPad?
iPad.
Those not that different.
Are you gonna make an iPad 3 that sucks? Wow. Isn't that different from that? Because I mean, think about it. Between the iPhone 3 to the iPhone 4, there was a big, huge difference. I mean, at least I think there was. You feel me? And then even from between the iPhone 4 to the 4S, I mean, one of the better things was the camera is Siri. The Siri is at least an upgrade. You get me? And then the iPad is gonna have the Siri. Oh my god, the iPad is better. So I guess the tablet is better.
Oh, iPad's better. Good. You know, so there is one tablet I would love to get, and that's the Asus Prime Transformer Prime, because it's a tablet, and then you can hook it up to a mount and turn it into a laptop.
Which one's, you remember it would be the one?
Okay, so you
Oh,
square it, and then put it to the third.
Where I have to plug in it right now?
So this,
Okay. But the 3 still is still in front of it, right?
yes,
It's just no, but it's in the other. Oh, no, wait. Would I have to use 4 in this case? Excuse me.
Yeah.
Use 4 instead of 64?
What you use here?
81.
Oh, yeah.
So 64, am I using 64 or am I using 4?
Yes, you're square 64.
I'm squaring, so I had it right.
Yes.
I finished the one you gave me, so you gave me 2 other ones. So I'm on the 3rd one.
You did 86 also?
Yeah.
Can I see? Good, and 63, where's that?
That's the one, no, 66 that here.
You subtracted it, right?
Mm-hmm.
Very good, because your dx was negative, good. Why is dx negative 1? Because 63 is less than 64. Okay? What cube root?
Yeah.
Alright.
No.
No, that's good. Edgar, what's the cube root near 66 now?
4.
I don't know what 64 squared is.
Be careful, Rosie, that's not what you have to start with. You gotta find a perfect cube near this area. So your perfect cubes are 1, 8, 27, 64, 125.
Yeah, that's what I'm using 64.
Okay, alright, you said 64 squared.
Yeah, because it's
Derivative.
negative 2/3.
So you're gonna square it and then cube root it. Okay, but, alright. I would just cube root it first and then square the answer.
Yes.
Isn't that asking you to do the cube root of 64 and then square it? The cube root of 64 is 4. And then 4 squared is 16. So that turns out to be just 16. Same thing as doing it like this. And then the cube root of this one. You should get 16.
Okay.
So I would do the cube root for part first, because you know that it's 4. And then square that to get 16.
So it would just be 48.
Oh, that's
Is it
basic.
196?
That's a
No,
base.
never mind.
That's a base on your mother for the.
Oh, no.
You go on Saturday? Yeah, well, oh yeah, you. Are you going on Saturday? Oh yeah, you.
Are you already then?
Yeah.
I want to, but
I thought he was talking to me. That's a.
I told Mr. Williams I would, but I don't think I'm going to be out here. And you guys leaving here what, around
I don't know.
What?
12-ish? Yeah, and interviews are from like 9 or 8 a.m. to like 2:30. I told Ms. Fernandez if like we get out of it early, I'd go with you guys for sure. I think Mr. Arnold's going to go.
What do I need to do to get
Mr.
the
Arnold
exact value of this?
66,
It's hoping.
Karen.
Okay.
96.
Oh, one
There
third.
you go.
You got 91 and 17.
Pretty close. 0416, 0412. Now, as the value gets closer and closer to the actual perfect cube or square, its approximation will be better and better. So if you pick the number like the square root instead of 86, you pick like, all right, so 90 and use 81, that estimate will be worse.
Oh, if I use 90 instead of 91?
No, sorry. If instead of 86, if you're giving the problem that said 90,
Oh.
then dx would have been 9, right? So that would be that hard. Let's do one now with volume and stuff, with error. So if you have a, say you have a, it's usually done with circular objects or spherical, because there's only one thing to take the derivative of, like r. Because if I do a cylinder, then the formula is pi r squared h, which might cause some problems along the way.
I did.
What do you think?
Friday.
Let's say we've got a basketball, okay? And the
Oh, nice.
the actual radius of the basketball, let's say diameter. The actual radius of a basketball diameter. Well, what is the actual? Let's look it up. All right, men's size 7 regulation. has a diameter of 9.4 inches. Okay. So the diameter of a basketball is 9.4 inches, traditionally. We know that when they make them, they're not always 9.4, right? They could be off by a little bit. We call that precision. So the precision on this, or the possible error, let's say the error on the diameter could be plus or minus 0.1 inches. So it could be 9.4, it could be 9.3, but it can't be more than 9.4, or it can't be less than. I'm sorry. It could be 9.5 by going up a tenth. It could be 9.3 by going down a tenth.
Oh.
So my range of possibilities for my diameter are 9.3 to 9.5. Just to keep that in mind, what's going on here. You don't need that for the math, but just keep it in mind. So my question to you is this. What might the volume vary by? How precise will the volume then be based on the diameter? Okay? So, let's go ahead and look. Here, I know volume for a sphere equals what again?
4
Wait, there's no hand of pi.
pi cubed.
You say how 4 years later, you learn that there's no pattern for pi?
That's why I was in the
Why do we always call pi
What's
irrational?
the point of the question?
So that's the volume. Now, my question though is this. I want to know how much will the volume be off by if the radius or the diameter is off by that much? Again, how far will the volume be off by? So I can't use radius clearly, I gotta put diameter, right? How much is the radius with regards to the diameter? How do we know? What is it?
1/2.
So if I put diameter instead of here, I should put. What is the radius really? How do I write it? I'm asking you.
So 1/2 of the diameter.
Good, so how do I write that? 1/2 diameter or just simply d over 2?
Yeah.
Okay? Alright. Now, I'm going to simplify it just to make it easier before I take the derivative. Let's simplify. It's going to become pi d cubed. What's 2 cubed though? So there's 8 down here really, isn't it? So let's just make this a 24. But if I make that a 24, what does this whole thing just reduce to? 1/6. So let's just write it like this. What the devil? Just write it like that, okay? So again, it would have been 4 over 24, but again, that's just 1/6. So that's the volume of the ball. So I can figure out what the volume is if I just plug in the diameter. The diameter is 9.4. I could always find the volume. But it didn't say find the volume. It said, how far could the volume be off by? The diameter could be off by 0.1 inch on either end. How far could the volume be off by? So how far is it off by tells us to find the small distance it's off by, dv. So take the derivative now with respect to d. dv dd. I know that sounds weird because it's diameter, right? But this is my integration part here, or this is my variable of differentiation. What I'm taking the derivative of. That's all that d is there. Not another derivative, okay? What do I get when I take the derivative of that? This is a constant, the pi over 6. How do I take the derivative of d to the third? Very good. Which clearly I can see reduces to actually what? What's 3 over 6?
Did you look at me at Baker? She's flirting with me.
What'd you say?
What would I reduce this to now?
Can you reduce it to pi over 2?
Very good. Because this is 2, that's a 1. Alright. So that's dv/dd. dv/dd. Okay? Move the dd up now, and you'll get dv by itself, which is what you're looking for. You're trying to figure out how much can the volume be off by. So now, at this point, we can plug in because we know the value of d. Oh my god, ever get an itch in your back?
Yeah.
We know the value of D, which is the diameter. What does that turn out to be, Rosie? 9 point. What is it? Good. What does DD stand for, though? What does that DD at the end stand for, really? Good. Remember, this is the change in volume, dV, or the part it's going to be off by. So dD is how far the diameter could be off by, which is what? Plus or minus 0.1. For now, I'm going to put 0.1. And then at the end, when I get my dV, I'll put a plus or minus in front to show that the volume could be above or below, depending on the scenario. At this point in time, what you want to do is just multiply through. See what you get there.
I got 13.879.
13, say again, 13
879.
Let's see, 9 squared is about 81, a tenth of that is about 8, 8 over 2 is about 4, 4 times 3 is about 12, and you got 13 each each? Sounds about right? 13 point what?
879.
What was it?
And that's going to be, my original was inches, so this is going to be inches cubed. Why is it inches cubed again? Good. Now, Rosie, here's what I'm going to ask you next. This is plus or minus, right? Depending on how my diameter's on. So, if that's plus or minus, then what do I have to do to it? That doesn't tell me, that just tells me how far the dV can be off. What could my volumes be? Because remember, my diameter could have been 9.3 or 9.5, right? What's the possible ranges of volumes? Tell me what you would do. Don't have to calculate, but what would you do here?
I don't know, I was thinking at first that you were gonna branch up, like, for one you were gonna plug in positive 0.1 and for the other you were gonna plug in.
Okay, that's fine, and you would get just this though. You would get plus or minus, the same thing. Well, my question for you is, what is the volume range going to be? This is just how far off it could be. How did I find the range of the possible diameters? I took the actual diameter, what did I do to it? So I had the actual diameter, right? So what do I need now? The actual?
Volume,
Why?
because you have the, how much you could be off by.
Good, so if you find the actual, you can add it or subtract it. So go back, plug in 9.4 in here now. Find the actual volume. Plug in 9.4 into the volume, give me the actual number of 4/3 pi r cubed. So again, this is my deviation here. That's my deviation. So if you find the actual volume, okay, if you find the actual volume, I could add that or subtract that value to it.
Who's your call that?
You know from far away, that shit doesn't look that bad.
She likes your kid.
Fernando?
Yeah.
She might be next door.
No, she starts with.
That 8.840.
Oh, 8.84? Not possible. Look at the numbers. Think about it. You're cubing 9. That's going to be like hundreds and hundreds. And then you're multiplying by what looks like 1 and 3. So there's got to be a few hundred. Parentheses, Rosie, don't forget. Put the 4/3 in parentheses before you multiply through. Because what you did was 4 divided by the whole thing.
You even have to look at your calculator, which is weak.
Okay, I got
$3,479.143.
Okay, so that's the actual volume. And now I have a possible deviation, right?
Yeah.
So what is the max and min going to be? How am I going to figure it out the range? Yep.
You subtract it. What do you want me to add first? Doesn't matter. Okay. If you subtract, it's 3,465.263.
Okay.
Let me see. If you add, it's 3,492.979.
Okay. So what this tells me is something as simple as this. And I know it looks like it doesn't mean much, but the volume of a basketball, based on the possible error for the diameter, could be as little as this or as big as this, in cubic inches, of course, which is really not that big of a number. Again, but the volume could be either of these values or anywhere in between them. That's an acceptable volume. And they do this in manufacturing a lot. They look at objects, they say, well, the radius could be having error by a little bit. What is that going to cause the volume error going to be? Well, the smallest the volume could be is this. The biggest it could be is this, based on the errors that we had a minute ago. Okay? It's not much of a difference, actually. 3,460, 3,490, 30 cubic inches is very small. Not a very big volume at all. That's differentials and linearization, because you're linearizing and you're taking the differentials here.
So that's like an example of the problem that we might get for that.
Yeah, it's going to be one of those two. You know, you're going to get one of each probably. Okay? So we did optimization in class. We did related rates after school. That was linearization.
There's curve sketching.
There's curve sketching, and then there's slope fields.
So good.
Yeah, slope field.
I'm not sure.
Slope fields?
I'm not sure what to think of that one. Pay attention to this. That's why I don't, that's why I'm sure. If I remember going over this.
Yeah. so
I could
that's
add,
what
so.
it does.
That's wrong. And honesty is the best policy. Jesus Christ in 30 minutes. Painful. That's why they don't need to. I recommend.
And then you go know to his manager.
Assume all units are 1 apart, okay?
Thank you for you. Already.
Red? Black one should work. All right, now if I want to find the slope or the slope field at each point, what do I have to do? You don't know? I agree. What do I have to do here to solve this problem, to find the slope field?
You have to plug it in point to point the
Yeah. So look at the coordinates, Rose. Here. What's the coordinate here? So if you plug 0, 0 in, what do you get? 0.
So it would be horizontal.
Yeah.
It would be horizontal for the x-axis?
Whenever,
No.
let's try and find the pattern, okay? What's this point here now?
0, 1.
You're doing that? Yeah, that's 1. This point here is 1, 0. So when I plug a 1 in now, it's 1 times 1, which is still 1. How do you know the point is 1, 0? If you listened, you would have heard me say, assume all units are 1 distance apart.
Okay,
So you can check the recording.
so if it's 1, like, it has to go positive. If it's
It's just-
-1, it would go like that.
And it doesn't matter what the slope looks like, really, it's just whether it's positive or negative that matters.
Okay, so it doesn't matter how steep it is?
Not really, but, I mean, realistically, yes, on the slope curve, on the slope field, you'll see that. But when you do it on the test, it's really positive or negative if you care about it. That's all that matters, really. Plug in 2, 0. 2, 0? 2 goes here again, Rosie. You're mixing them up. I'm sorry, no, it'd be positive 4. 2 squared is 4 times 0 plus 1. 4 times 1 is 4. You did 4 plus 1. Okay, it's all right. It would be steeper, so if I want to draw it steeper for now, I can. Because the derivative is steeper there, or the slope is steeper, but it doesn't matter really. On the other side, Rosie, what about negative 1?
Okay. What?
Yeah, it's still just 1. Because this, even though it's negative 1, you're squaring it, aren't you? So what generalization can you make already? Look at the function. What generalization can you make? Oh, come on, people.
The x-axis would be
She's
positive?
answering.
Both of you.
Oh.
What generalization? The x-axis would definitely be positive except for the origin there. But a better generalization than that.
Negative is 0. Anything above the y-axis is increasing.
Better generalization. Come on. Guys, look at your values. Aren't both coordinates squared?
Yes.
So are they ever going to be negative?
No.
They're never going to be negative, right? When you square something, it's always positive. So all of your slopes are either going to be 0 or positive. You want to say increase, that's fine, but just talk about the slopes. All slopes are greater than or equal to 0. Okay, dy, dx, the slopes, will always be greater than or equal to 0. Because again, it's only 0 when x is 0, which is here, which is here, which is here, and here, and here. Remember, x is 0 along the y-axis. So you made the misconception before you did along the x-axis. Everything else, Rosie, no matter where you put this.
So what if it was x cubed, y cubed?
Well, that's different, because a negative cubed is a negative. But this happens to be squared here.
But could you say, make the same?
No, you could not, because it could have negatives. If it was x cubed, y cubed,
No,
you
I'm
could have
saying,
negatives.
but that it would, everything would be negative no matter where it went.
No, because if you might get a negative negative, which will get you back to a positive.
Oh, okay.
It's always unique to each situation.
Okay.
So in this case, here's your generalizations. dy dx is always greater than or equal to 0, and dy dx equals 0 for x equal to 0.
Wow.
Is this something we would have to have?
Part B.
In order to get?
Part A is graphing, part B is coming up with these statements. Okay? So again, graphing it is only the first part. The second part might say, make a statement about the derivative for all values. That's the first one. Then make a derivative about the statement for the domain. All of x is equal to 0, dy dx equals 0. You could also say, even better, dy dx is greater than 0 for x not equal to 0. It's the complement of that statement, right?
But would that include the bottom statement?
Yeah, I mean, this upper statement is general. This says when x is 0, the derivative is 0. And this says when x is not 0, the derivative must be positive. And look at all of our other points. They're all positives. Now, part C would have been what we did the other day. Remember with the particular solution? So you would have to, move the y squared plus 1 down, move the dx up, integrate both sides. That's the other one. Okay? I know it's itching, sorry. Curve sketching? Last one. My voice is running out. I just can't keep talking.
Yeah, it is.
Tomorrow will be an easy day for me. All the juniors work. You guys are taking assessments. Physics is a big test, if you heard before. So I don't even teach tomorrow at all. It's like a day off. I have to grade all your stuff now, so.
Is Karen
Not really. What?
Because Karen gets up like 60 times before she actually finishes the test.
Right. She beats your butt every time, big guy. Be careful.
Because she talks to you.
If she forgets it by the time she graduates, well, what's the point of being an A?
She's not going to forget.
She's not.
She works her butt off, guys. Come on. All right, let's go. So in this problem here, we want to think about curve sketching. So what could be an example of a problem you might see? What have we done with curve sketching before?
If I look at find the original to the first variable.
Okay. Or, good. What else?
You've given us a graph with we don't even know.
Okay, you can do that.
Find everything.
Find the others, good. So if I give you the original, find the first and second derivative graphs. What else? I've done other ways too.
You've done the derivative as well.
And you have to find the original. But besides graphs, what else am I
You
using?
give us the equation, and
Now with these, I don't usually give you an equation.
give us the second equation. Oh, you give us that chart.
A table. That might be a table also. And I told you about whether it's increasing or decreasing, how do you up, how get down, all that fun stuff. So, which of those three do you want to start with? Well, we're going to do one of them for now. Either we have the original and find the other two graphs, have the other two graphs, find the original, have a table, graph the original.
The first two is find the original and acceleration.
Given the first
Given
derivative,
velocity, find position, and acceleration.
okay, fair enough. So, I will give you velocity in the middle, and then we'll find the graph for position up top, and for acceleration down below. Alright, so let's say the graph of velocity looks like let's say that's a graph of velocity. This is on the x-axis over here. Let's say that's our graph of velocity as a function of time, sorry. We want to find position. We want to find acceleration. Which way do you want to go first? Doesn't matter. You want to go up or down? Down? Okay, Rosie, what's the relationship between velocity and acceleration?
Velocity is the first derivative and acceleration is the second.
So the derivative of velocity, doesn't that just become acceleration? So if I look at this graph, I want to look at all the slopes. Rosie, tell me, from here to the origin, what is the slope of that line? 0. So the slope of this is just going to be 0. Oh, that works out pretty well. Next, Edgar, from here up until here, the slopes are all what? And then from here, Edgar, until here, so here all the way until there, they're all going to be negative, right? So this is going to be all positive slopes. Okay? Now, when I have a minimum or a maximum on my original, it means that I have a root on my derivative. Because remember, to find the min and max, you set the derivative equal to 0, which is the root there. So that's the root there.
Minimum as well?
Say again?
Is it for the minimum as well?
For a minimum as well, but what's that? That's not actually a minimum. What is that? Cusp, which there is no derivative, remember? It's not defined. So I have to talk about that.
Okay.
Now, before I just start increasing right here, what are you going to notice? What is this right here, guys? What is this called?
Origin?
Sure. It's a corner. This is a corner here. Take a look. This is a line. The beginning of this is also a linear function. That's a corner right there. A corner, do you have a derivative though? You don't, because look, there's no derivative, and then out of nowhere, there's a positive derivative. So this derivative will start like this here, and it's going to increase. The slopes are going to then decrease, so we're looking at something like this. So see that discontinuity there? That comes about because of the corner. Again, take a look. The slope is positive. Watch my pen. Slope is positive, 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 and then what happens to the slope? It starts to decrease, doesn't it? Until the slope becomes 0. That's this graph here. The slope is positive, 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 until around here, when it starts to decrease, the slope. So then it starts to decrease until it gets down to 0.
So for corner and cusp, you don't have derivative.
Correct.
Okay, correct.
Doesn't matter. If you have a corner or cusp here, you don't have a derivative here. If you had a corner or cusp up top, you don't have a derivative here, and therefore you don't have one here also. So as many derivatives you have, none of them will have it.
Okay.
After that, we see that this is a flat line. Then the tangent is negative, so it's going to be down here. It's becoming more negative, more negative, more negative, until it becomes almost vertical, doesn't it? So this is going to become more and more and more negative all the way down. So what is this dashed line here really? What's the word for that? Sure, it's a discontinuity. What is that vertical line called? Think back. What is it? An asymptote. Because here's how we can tell, Rosie. Watch. See how this becomes really negative or really steep? Once I go to the other side of the cusp, isn't it really steep in the positive direction? So now it's going to come down from up here. So the slope is really positive until what happens here? It starts to flatten out, right? Until it flattens out at the end. So this one's going to look like this. Again, the blue line that's angled there is showing the slope is really steep. So it starts as a really high positive slope, and then the slope gets less and less and less until it gets to zero slope, which is right there at your root.
So similar to the first section of the graph?
Yes, yes. But the idea is this. The vertical asymptote exists in the derivative when you have a cusp. When you have a cusp in the original. This is the derivative at the bottom. This I'm considering to be the original.
Is it always like that?
Yeah. Whenever you have a cusp, because think about a cusp.
Yeah.
One side has a negative slope and one side has a positive, really, right? So that's what you're seeing there. Well, one of them is really negative, down to negative infinity. One of them is really positive, or up to positive infinity. So this part of the graph really extends up to positive infinity like that. Okay?
So there's an arrow?
So there is an arrow on both of those, yes, because it does become asymptotic. So we'll go on forever then. That's the derivative from the original. Now let's find the integral from the original. Remember the integral? Okay? So take a look here. If the slope is 0, I could have many different things here. If this tells me that the slope of this line up top is 0, so it could look like this, it could look like this, it could look like this, like this, like this. All those slopes are 0, aren't they? So I don't know which one it is. So for this one, you have to pick an arbitrary value there. Okay, pick an arbitrary point there to figure it out. So it does not matter right now unless you're given an initial condition. If you're told, if you're told something like this, then you know x of 0 is 4. So you know that that point's there, so this must look something like that. X of 0 means when x equals 0, up here y is 4. Okay? I'm going to take x and y as in, sorry, when t equals 0, x is 4. Or when the x-axis is 0, the y-axis is really 4. Then what do you notice? Your derivative is 0, it's still 0, and then it starts to get positive, right? And then the derivative is positive for a while until here, then the derivative becomes negative, it's still negative, then the derivative is positive. So here, since the derivative is positive from here to here, we have an increasing function. Okay? And remember, the root, which is right here, indicates a max or a min up there. Gotta work backwards now. So this function is gonna, how do I move this up instead of down?
I didn't know what they drag it down.
How does that not work? Perfect. Okay. So that was the derivative, right? Again, now we're going to the original. So this part of the portion or graph is increasing because the derivative is positive. So this has got to start going up. Okay, it's increasing until here. And here it's going to have its maximum. It's going to plateau. Okay, there's the maximum right up there. Then the derivative becomes negative, doesn't it? It becomes negative right there. It's got a little bit of a cusp here, and it becomes positive again. So the derivative is negative, which means it's going to start to decrease real quick. It's going to decrease. It's going to continue to decrease. It's still negative, and then it becomes positive, so it's going to start to increase again. So right here, I'm going to have a minimum. Again, it was decreasing, and then the function started to increase after that. So it's decreasing, 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 still decreasing until I get to here. Still decreasing. Then it starts to do what here? Increase. This is all above the axis. Since it's above the x-axis, it means that the function is increasing. So it then dips down and it starts to increase again. Again, when the derivative equals 0, which is, just to point it out, the derivative is 0 here and here. When the derivative is 0, you have either a min or a max, or an inflection point, depending. In this case, though, it goes from positive to negative, which means increasing, then decreasing. So there's a max up here. Then it goes from this whole portion here being negative to then positive. So this must be a minimum, because it's decreasing, and then it starts to increase. There's the minimum. We don't know too much about that minimum, though. We don't know what it's really going to be, okay, based on these values alone. Okay? It's tough. It's not an easy concept. That's one of the hardest things, curve sketching. It really is. It's not easy at all. A lot of it comes down to just practicing more problems. Okay? I did put a ton of problems in your syllabus. Posted it online and on Facebook, both. Okay? Look at the syllabus. Make sure you look. See in your textbook what you want to look at. A lot of stuff for tomorrow. 5 concepts. You're ready.
Is that a quiz?
I know it's a test pretty much. I mean, I'll take the whole period for sure. But our tests are usually 2 hours, so it's like a half test. Good. All right? Thanks for coming in, Rosie. As much as you can, keep doing this, please, all right?